Hey guys, your boy Chill here. Welcome back to Advanced C++. Today, we're going to complete the other half of the smart pointer coin. Yes, we're talking about shared pointer today. And shared pointer isn't just like a single thing. It's a little bit of an ecosystem. So I'm going to break it down into two parts. Part one, we're just going to learn about, how it works, how to use it, how not to use it, some basic examples. And then in part two, we're going to go a little deeper. We're going to look at the internal mechanics of shared pointer, its auxiliary utilities. But before we dive balls deep into shared pointer, let's take a little quick recap about unique pointer. The main claim to fame for unique pointer is the automatic deallocation. We can use the stack, we can use the scope to control the deallocation of dynamic resources, and that, makes sure that we don't drop anything on the floor. We always clean up our messes when we're done with them. The second piece of the puzzle is that unique pointer prevents copies. And that's super important, right? Because if you have a unique pointer, it's going to call delete when it goes out of scope. If you make a copy of that, now you have two unique pointers pointing to the same memory. They're both going to try to delete it. One is going to succeed. One is going to shit the bed. So you prevent copying, and that's the unique part of a unique pointer. But you still allow move operations, and thus you can use these things, these unique pointers in containers, and you have to sort and shift them around. It will move them rather than copy, and everything will just work. The third great thing is that you can supply a custom deleter, and you can change what operation happens when the pointer goes out of scope. By default, it just calls C++ delete. But if you're managing some special resource that requires a particular function to delete it, you can manage that with unique pointers as well, as long as you supply a custom function that calls the cleanup function. All right, let's say we got some kind of owner object. It has a unique pointer that owns some resource on the heap. And when this object goes out of scope, when it gets destroyed, this is going to get freed automatically. Everything's nice. Now let's say we've got a second object. It's just an observer. It doesn't want to manage the lifetime of the resource, but it does want to keep tabs on it. So it's going to maintain a raw pointer, and that's fine. It couldn't maintain a unique pointer because, you couldn't copy this unique pointer to here, and you wouldn't want to transfer it because the owner would lose ownership. So this is fine. And as long as the observer doesn't live past the owner, it's okay. If the owner dies first, this is going to get destroyed, this is going to get destroyed, and now you've got a dangling pointer. That's bad. But now let's say we have a second object that also wants to own the resource. How does that work? Well, we can look at it. If we look at the graph here of the lifetimes of the objects, if it looks like this, if you have object 1 owns, and then at some point object 1 goes out of scope, but object 2 wants to begin to own, you can do that easily with a unique pointer. Object owner 1 and owner 2 both own the resource with a unique pointer. When it's time to pass the torch, you can just do a move from this unique pointer to this unique pointer. You transfer ownership. Then when this one dies, it's not going to delete the resource because it's now owned by owner 2. So that works for this kind of life cycle. Now, what if there's some overlap between owner 1 and owner 2? In this case, well, if owner 2 is guaranteed to live past owner 1, you could still do a unique pointer here, transfer, but you would have to switch owner 1. You would have to switch it from owning with a unique pointer to just using a raw pointer here to maintain a reference. So you would have to have two modes, and that's kind of nasty. You could do it, it's not the greatest. Now imagine the situation where object 1, maybe it's deleted while object 2 is existing, or maybe object 2 is created and then deleted, and then object 1 is deleted. So you don't know the order of which one is going to die first. And maybe it's not just object 1 and object 2, maybe there are 1,000 of them, and they're all trying to own this resource. And you don't know the order, and you don't know the overlapping of which ones are going to be alive at the same time, which one is going to die last. It's crazy, and it would be crazy to try to manage that, which one. You'd be playing musical chairs all the time trying to figure out which one is the owner and which ones are just the observers. Enter shared pointer. Shared pointer, one of the main distinctions between shared pointer and unique pointer is shared pointers can be copied. So Object 1 gets created, creates a shared pointer, initializes a resource. It's owning the resource. Object 2 comes into play. It also has a shared pointer, and this is copied. And now they both own the resource together. So what happens now when object 2 is destroyed? It's a smart pointer, so it's going to be destroyed and it's going to remove this resource, right? Wrong. It's not going to do that. The second and the most important thing about shared pointer is that if there is any other shared pointer owning this resource, it will not free the memory of the resource. So when object 2 goes out of scope, object 2 dies, this shared pointer reference goes away, but this guy keeps going until object 1 dies. When object 1 is dying, shared pointer checks, are there any other references to this resource? No. Okay, then when we die, we turn out the lights. The last one out turns out the lights. So in this scenario here, object 1 is going to be the one to do the deleting. But in this scenario here, object 2 is going to be the one to do the deleting. So with a shared pointer, you can never have that situation of having dangling references. The shared pointer system keeps track of how many things are referencing the resource. And when that goes down to 0, then it's time to say goodbye. Exactly how it achieves that is something that I want to get into in part 2. But for right now, all you need to know is that the last one to go turns out the lights. So shared pointer enables copying, and that's the mechanism by which you share resources with shared pointer. But it also supports a move operation, and that's could be useful if you look at this scenario here where there is no overlap, there's just passing of the torch. Then you would be better off doing a move rather than a copy. Move for shared pointers, move is going to be better performance than a copy. But again, I'll get into those details in part 2. All right, now let's play around with objects and resources a little bit, get a feel for shared pointer. So we're going to start off with a basic setup here. We've got a resource type, and it's a little noisy. So it's constructors and a destructor will print things out when stuff happens. This resource is just for our purposes, just going to own some simple data, a string. All right. And then we've got an owner class that will own resources or will own one resource. So it just embeds a resource object and its constructor takes a resource object by value. All right. So let's create some stuff. I'm going to create a resource R1 and let's initialize it with with a string. We'll go with the good old butts. That's my go-to. Now we want an owner. We'll call this one own1, and it has to be initialized with a resource. So we'll put an R1 in there. And let's create an owner own2 as a copy of own1. So what do you expect to be printed out from this? Make a little prediction here. Let's test out your fundamentals of C++. Now here's what we get. Is it what you would have expected? Resource is alive. All right, that's our constructor here. Resource is alive by copy. That is when we call the constructor of owner, we are going to copy the resource into this parameter here. Then resource is alive by copy is copying from this parameter into the embedded resource inside of owner. Fine. Then resource is dead. That is this argument going out of scope at the end of the constructor. Then resource is alive by copy. That is this one here. When we copy from owner 1 into owner 2, we are going to copy the resources. Then resource is dead is the resource in own 2 being destroyed. Dead is the one in own 1 being destroyed, and dead is the original resource being destroyed. Okay, so far so good. Now we could make this a little more efficient. We could eliminate some copies there. We could say, well, this argument doesn't need to be maintained, so we can do move into the member there. And that is going to be more efficient. If we run this, we're now going to see at least, I think, one fewer copy that's been replaced by a move. And one of the resources destroyed was now just a husk. so we're a little more resource efficient. We can also move from R1 into own1 because R1 isn't needed after this point. And now we're seeing less copies being made, less resources being allocated. We're getting efficient here. Technically, we could also move from own1 into own2, but let's assume that we wanted two objects for a reason. We're going to do something with both of them. So we normally wouldn't do that, but you get the idea here. But let's say that our owners, they aren't actually modifying the individual resources. They could, for all intents and purposes, all share the same resource. Just to make things a little spicier, I've added a bunch of owners now. So now we're going to see, lots of copies being made and destroyed here. But if they can all share the same instance, that's a waste. So let's make them share the same resource using shared pointer. Declaration here, same idea as unique pointer. And same as unique pointer, this is very important, so pay attention. When we are going to accept a resource as a shared pointer, we're going to accept it by value. Because every owner that receives a shared pointer here is going to want to make a copy of that pointer to have its own shared pointer to the object. So by accepting by a value here, you allow the caller the choice of either passing in by value, in which case a copy is made at this point, or they can use std move to move a shared pointer in which case you're transferring ownership. So this one declaration of a constructor here supports both increasing the number of references to a resource, which is sharing, or transferring ownership. And then after we have our shared pointer, we're just going to move that into our member here. So now when we make our resource, let's make it as auto pointer to resource, which is called PR. And just like unique pointer, we have std make shared. Make shared is even more important than make unique. There's very little difference between make unique and just creating a unique pointer from the constructor. But make shared has an actual difference from creating a shared pointer from its constructor. And I'll talk about that in part 2. So we're going to make our shared resource. We're going to pass in the name of the string. We'll go with the classic one. And now we're just going to copy that pointer into own1 like this. So now what do you expect to be printed out when we do all this? Well, the resource was created and the resource was destroyed because all the owner objects, because they're all sharing the same instance of the resource, it's only going to be created once at the very beginning here and destroyed at the very end here when all of the owners release their references. Now remember, I told you the way that shared pointers work is the last one to leave turns out the lights. How do you know you're the last one to leave? The answer is that the shared pointer system maintains a count of how many shared pointers are referencing the single object. We can actually access that reference count. It's called the UseCount. So we go down here, UseCount, and we can get how many things are referencing the resource. So let's print out the UseCount after we create the original shared pointer. And then after we create one object, let's create this next two objects in a scope here. We'll check the UseCount after we've created these two. And then after we leave the scope, then after we create own4, so make your prediction. What do you think you're going to see here? So resource is created, we got one reference. Then we're going to construct an owner. It is going to get its own reference to the resource. Then we're going to construct two owners. They're going to get their references. Then those owners are going to be destroyed. Their references are going to be removed. We're back down to 2. We create one. We're back up to 3. And then when we leave this scope, all the remaining references are going to be removed. And then the resource is going to be destroyed. Now, similarly to the above situation, because we're not using this pointer after this point here, we could just be a little more efficient and move it into own1. Now you may be wondering, why do we get all zeros when we print out the UseCount? Well, think about it for a second. Have you figured it out? The answer is because we have actually moved that pointer into here. This variable PR is now holding an empty shared pointer. So of course, if we check the UseCount on an empty shared pointer, it's not going to give us any useful information. Once we move out of here, PR has now lost tabs on the resource. It no longer tracks that resource. So if we still want to print out the use counts, we could add a member function to owner. Then we could replace all these guys in here. Now it should be more like what we would expect. We create the shared pointer. We got one reference. Then we move that. So instead of sharing, we are transferring ownership. So the number of references remains at 1, then it goes up to 3, then it goes back down to 1, then 2, and finally everyone is dead. Clean up. And of course, if we're going to do this, we don't need to play this hanky-panky. We could just use the return value of make shared directly here to create our owner, own1, and that would work the same. Now let's say we want to give the outside world access to the stored resource inside of owner. How would you want to do that? Well, you might say, well, the resource is a shared pointer to resource, so I'm just going to make a function that returns a shared pointer to the resource. And you can do this, just return res, but it's not what you should do, right? Because what are we trying to do? We want to give the outside world access to the resource, to just, call some functions on it, do something with it, get some information. Does it need to know about the relationship, about how we're owning that resource? No. So then don't leak that information. And furthermore, I've already mentioned this once, but copying a shared pointer means adding another reference, and that isn't free. So if you just want to give access to the resource object itself, then you should just return a reference to the resource. And then we can just dereference the shared pointer here, and everything works fine. If we don't want to let the outside world modify our resource, we can return a const reference, and that's even better. But don't deal in shared pointers or smart pointers at all unless you need to, unless whoever's calling that function needs to know about how you're owning that for whatever reason. Similarly, let's say you want to create a function to allow someone outside of owner to share in the ownership of the resource. How would you do that? Well, you might say, okay, well, I'm going to return shared pointer resource, but let's return it by reference because then we don't copy the resource. So we'll call the function share resource, and then we can just return res. And now when the outside user calls share resource, they've got a reference to this shared pointer, and then they can copy it. Well, don't do that. Don't give the outside world a reference to your shared pointer, because what they can do, you would expect, okay, they're going to call shared resources, and they're going to get a reference to your shared pointer, and then they're going to copy that into their own shared pointer, and that is going to increase number of uses on that resource. And indeed, that is what happens. Here we see that the number of uses has been increased. But that's not all the outside world can do with your newly created function. They could also do shared resources, get a reference to your shared pointer, and then call reset. Now what happens? They've got a hold of your internal shared pointer, they release that, they destroy the resource, and now none of that other copying ever happens. Well, the copying does happen, it's just that all that's being copied is an empty shared pointer. So this is a terrible idea. If you want to share a resource, if you want to give them a new instance of shared pointer, just return by value. The caller wants to share, give them a shared pointer by value. The caller wants just to access the thing, give them a reference to the thing. Don't even bring shared pointers into the equation. If you do this, and then some donkey calls reset on the shared pointer that was returned, what's going to happen? It's going to, reset that one shared pointer, but your internal shared pointer remains intact, and the rest of the process proceeds as you wanted. The resource only dies at the end. Well, I think that's the basics of shared pointers all covered. Let's just look at a few small random things. So you can actually create a shared pointer from a unique pointer. There's no problem with that. Why would there be? You're just taking the pointer that the unique pointer owns and transferring it into ownership by a shared pointer. See, it builds fine here. But you should still prefer make shared, because if you make a shared pointer with make shared, it is more efficient, and I'll talk about that in part 2. But it's a thing. You can transfer ownership from a unique pointer to a shared pointer. Cannot do it the other way. You cannot transfer from shared to unique pointer. Think about that one. Why do you think that is the case? You can compare shared pointers, and they compare whether those two pointers own the same resource or not. They don't compare the values. So here I've created R1, shared pointer. R2 is a copy of R1. They both refer to the same resource. And then R3 is a separate resource, but it has the same value. And if we compare them, we see as expected, the first one compares the true, the second one is false. Now by default, shared pointer manages the memory as a C++ allocated dynamic memory block. So it assumes that the memory is allocated with new, and when it's time to clean up, it calls delete on the pointer. But you're not limited to that default behavior. You can manage any sort of resource you like, and you can supply a custom function that provides the cleanup behavior for your custom resource. So here, I'm just going to give you a simple example here. We're going to call a function from the Windows library for allocating dynamic memory, local alloc. Now, if you allocate with local alloc, you can't free with delete. That doesn't match up. You've got to call local free. So what you're going to do is you're going to create a shared pointer. We're going to use the constructor this time. And to the constructor, we pass the pointer to the memory. And we also pass a pointer to a deleter function. And we just define that using a basic lambda. It takes the pointer to the resource and it calls local free on that resource. And if we run this, we see we set up the deleter. We set up our shared pointer. We can use that shared pointer, store something in memory there. We can print it out and we see, yeah, indeed it is getting printed out. And when it's time to leave scope, if I try to step over here, it's going to trip this breakpoint one more time because it's calling local free before we leave. And with a little bit of clever thinking, it's not hard to see that you're not limited only to memory allocation and deallocation. Any sort of functions that can clean up using a pointer can be used for this. So you could use it, for example, to wrap a file resource that is managed by a pointer. You can put a shared pointer to wrap it. You can pass it around. And when everyone is done with it, it'll automatically close that file handle. It's just one example of another way you could use this. Now you might be wondering here why I'm calling the constructor directly, why I'm not using makeShared. And the fact of the matter is, if you are supplying a custom deleter, you cannot use makeShared due to the way that shared pointer is implemented. But if you're willing to go out of your way and create a custom allocator, then you can do something that's basically the same as makeShared. You can call allocateShared, which requires you to pass in a custom allocator. And that allocator will contain the information needed to also clean up that resource type. And then you can, basically do the same as makeShared, but with any kind of resource you want. But it's an advanced topic, so I'm not going to go into it in this video. Alright, so that's the main points I wanted to touch on in this video. Let's do a quick recap of the important points. The do's and the don'ts. So first thing, what should you be doing? Use makeShared. Don't use the constructor for shared pointer. It has significant advantages. They will be talked about in more detail in part 2. Whenever possible, when you're transferring resources, instead of copying and then deleting the origin, just move that shared pointer. It's going to be more efficient and cleaner. Do use pointer value semantics when you want to share ownership, right? When you want, when the outside person is trying to get a reference to something that's being held, you can return a shared pointer by value. And when you're constructing something that needs to share ownership, it should accept a shared pointer by value. And when you're not dealing with ownership, do use the underlying type T. Return a reference to T or a const reference to T. Don't bring shared pointer into the equation if it's not necessary. Don't use smart pointer if you're only ever going to have one owner at any given time. If the owner is unique at any given time, that's probably a big hint that you should be using a unique pointer. Unique pointer is basically free, has zero overhead when optimizations are enabled. Shared pointer has some overhead. It has to deal with references and track them. But beyond the optimization thing, it's not good communication. If someone sees you using shared pointer, in their head, they're going to assume there's some sharing of resources going on. And if there isn't, you're lying to the people reading your code. The other main don't is don't grant access to the encapsulated shared pointer. It's a recipe for disaster. It's a corollary to these two guys here, right? So if you want to deal in sharing ownership, then you should return a shared pointer by value. And if you want to deal with the underlying type, don't bring shared pointer into the equation at all. Now for the homework, I'm going to bring you guys back to the inheritance stuff that we did in intermediate. This code base here with the meme fighters. I've cleaned it up a bit. I've split it up into separate header files for, all the different classes. So it's a little better organized for jumping around. But it's the same code as you had at that time. And what I want you to do here is very simple. Just identify where you might see resources that are being shared and use shared pointer to share those resources. I'm not going to tell you what points I have in mind. I want you to think about it and do your best. And then I'll do a solution video where I show you the shared resources that I identify as targets for sharing and how I implement sharing using shared pointer. But yeah, that is shared pointer. And I've only done a simple made up example here. But I hope you can see, this is actually something that is very useful when making real software. And if you want concrete examples of how this stuff can actually be used, you don't have to go far. I use it all the time in my other code bases. Look at the hardware 3D stuff here. We've got drawables, right? And a drawable is just a big container of bindable things that are bound to the rendering pipeline and used for rendering. And they're all owned by shared pointers because many drawables might use the same bindables. So these drawables own their bindables via shared pointer. And then there is a central bindable codex that maintains a registry of all the bindables that you could want, and you can resolve them out via a unique ID as it's a string. And I use that pattern quite a lot in a bunch of different places. That's only one example of how you can use shared pointer. But that's going to about do it for part 1. In part 2, we're going to dive deeper. We're going to look at how the shared pointer mechanics are actually implemented and what that means for how we use them. And we're also going to look at some utility functions and classes that go along with shared pointer. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more advanced C++.